Is this working? Yeah, I guess. Okay, so today's discussion session will be taken by two TAs, myself and Shin. Some logistics before we start. So the midterm 1 is this Friday, Feb 8. It is in GH242. We have also overflow rooms. So we have two rooms, PET 103, Solis 109. I think the links are up on Piazza. If you want to basically go to those classes, those lecture halls, you should sign up for that. Okay. And we will also release the seating chart for the midterm. It will be available, and you will have to occupy the seats according to that. I guess the practice problems are already up on Canvas. Is that right? Okay. And we'll also conduct a review session tomorrow for midterm. That will be, I think, maybe in the evening tomorrow. The exact time we will share by the end of today. Okay. Is there any other question before we start? Cool. Then, so today we will go over minimum spanning tree problems. I guess this is a topic that was covered last week in detail in the lectures. So today we will see specifically this topic. We will go over two problems and we will see how to solve those problems. Okay, sounds good? Okay, so this is the problem. So you are basically given an undirected graph G. It has its own vertices and edges V and E, and you're also given a subset S of V. And you want to check if it is possible to form a spanning tree of G where all the vertices in S are leaves. Okay, and if not, you have to return not possible, and if it is possible, then you have to return a lightest such spanning tree. Is this question clear? So what it basically means is something like this. So let's say this is our set S. So this will be something like V minus S, right? So what we are saying that these things here, they have to be the leaves of the spanning tree, and you want to cover all the vertices given in S. Okay. So if you have, so you will have an MST or a spanning tree something like this. Okay, so let's say S1, S2, S3 are the, let's say for example, these are the vertices. So they should only occupy these leaves. Okay, is it clear? Any questions? Okay. Well, let's see some examples before we move forward, so you get a little bit more clarity what we are exactly looking for. So in this example, B and D, they are the subset. Okay, so these are the subsets that you want as your leaves in the spanning tree. So can you make a MST out of this one such that it satisfies all the properties, and it has to be a minimum spanning tree? Maybe take some time. And so this is B and D. It only has to have like one edge incoming to it or outgoing from it, right? Yeah. Yes, exactly. Sorry, which ones? So in this example, it's not leaf, but when you create MST, you only have V minus E number of edges, right, in the MST. So in that MST set, that has to be a leaf, right? All these edges won't be there in the MST, right? So if you create an MST out of it, it has to follow a condition that these two things, these two nodes, they have to be leaves. So maybe like something, so let's see like what will be a valid such spanning tree. So I'm going to create an example out of it, which might not be an MST, okay? So one such example could be this thing, A, C, B, and then D, E, right? This is a spanning tree, right? and it also satisfies the property that B and D are the leaf nodes. So what is the sum of this spanning tree? It will be addition of these things, right? It is 13. Right. So do you think it is the minimum spanning tree possible? It satisfies all these properties. Can you do better? Sorry. I mean, like we have to minimize. It's a spanning tree indeed, but it might not be a minimum spanning tree, which satisfy these property that B and D they have to be leaves. Maybe you can create one more spanning tree which will give you a cost less than 13. Replace BC with, oh, okay, let's try that. So you are saying something like this, right? And then C, D and E, right? So what is the sum in this case? It's 10, right? So yeah, it's better than that. And I don't think we can do anything better than this one. So for this example, that MST, that spanning tree will be the answer. So let's see, I guess this is exactly the same that we just created, right? Yeah. So let's take one more example. What is the solution for this one? Is it even possible to make an MST out of it, such that it's a leaf, such that C is a leaf? Yeah, I see the solution. Yeah, it's not possible, right? Because in no situation you can just make one edge going from C, which covers all the other vertices, right? So yeah, so it's not possible in this case. So how will you solve this problem? So these are like two questions that you have to ask yourself. Like these are the two things. So how do we know that such an MST exists, right? So we saw two examples. In one case it existed, in another case it didn't exist. So first thing is that. And the second problem is, if it does exist, then how do we find the lightest one, right? Maybe you can take some time and like discuss among yourself, and let's discuss after that. Any idea, any intuition, like how we might approach? Maybe even if just a first step, might not be the whole solution. Yeah. Kruskal might work, but the property that these S set, it has to be leaf, that might not be fulfilled in case of Kruskal, right? It will definitely give you a minimum spanning tree, but the additional constraint that we have here, it might not be fulfilled there. But we'll have to use Kruskal in one way or other for sure. But you might want to like think like how we can like modify it a bit, you know. Maybe delete some edges first, then run the Kruskal, right? Something like that. Yeah. Yeah. That's actually a good idea. So we are going to do something on the same line, but we will see the exact details in a bit. Any other idea? Yeah. Wait. So, so in this example, so you are saying like maybe so make this a directed graph basically, right? So for this edge, we will make something like this, right? And then what was the next step? Like for all these subsets, what do you do? Okay. Uh, oh, so for this vertex, you remove all the edges, this thing. You remove this. Oh, that means outgoing from it. That's what you meant, like these ones, right? Let's think about it. Would it work? And then what do we do after that? Mm-hmm. So basically, you're trying to find a MST in this one now. Would it work? So you have essentially made these red vertices as your sink. It might work. I don't know. I'm not sure. It might work. So we'll have to like investigate a little bit more about it. The solution that we have is a little bit different. So this might work. I'm not able to think of any counterexample as of now, and I might think it might work because you are essentially making your red nodes as the sink. So once you reach that point, you have no way of going out of it, right? So it might just work. I'm not exactly sure right now. So let's see the solution that we have here. So what it is saying is you create a new graph G prime by copying all the vertices except for the vertices in S. Okay? And then what you do is you first check if the new graph G prime it is connected or not. Right? If it is disconnected, that means it's not possible. Right? That's what the algorithm is saying. But if it is still connected, then what you do is you run your Prims or Kruskal or any other MST algorithm on that, and you find the MST T prime. And then what you do, for every vertex in S, you find the minimum unit edge going from that particular vertex to the set to the T prime thing. And then you connect these vertices one by one. That's what it is saying. But in this case as well, if you find any vertex such that you do not have enough edges to connect it to this T prime, then that means it's not possible yet, right? So in that case as well, you return not possible. So do you think this will work? Is the solution clear? Yeah. Oh yeah, sure. So what it is saying is, so let's take this example that we had here, the one that works. Okay. So, or we can create a new one. Let's create a new one. So we have A, B, C, D, and E. Okay, and let's say this B and D are your vertices in your set S. So what it is saying is like copy everything here as it is, except for these nodes in S. That's it. So you don't copy this D and B. So that's your G prime. And then you run your MST on this graph here in G prime. So once you have your MST, so in this case it's pretty straightforward. It's only one MST, one possible thing. So after that, what you do is you go to this set S. You take a look at one node at a time. For B, you check like what is the shortest. I did not label it, but let's say this is the thing here. Okay, so for B to A is the shortest edge connecting B to the set G prime, right? So we will connect B to A, and then we'll go to D. For D it will be 4, right? So it's saying this has to be the solution. Is it clear? Yep. So how will you prove this? You already had a peek at the solution, I guess, but how will you prove these things? Like, so in the lecture as well, you have seen MST, like the proof for MSTs and such. So how do you prove these things? You generally prove two things, right? First, you prove the existence. That means you want to show that the algorithm returns not possible if and only if it's actually not possible to create such an MST with all the properties mentioned satisfied, right? That will be existence. And the second thing to prove is the optimality. That means the spanning tree that you are getting from your solution is indeed the lightest such spanning tree. Okay? Does that make sense? So how do you prove the existence here? So you have to prove these two things separately. So how will you prove the existence? So what do you generally do in case of if and only if? Yeah. Yeah, that's right. So we'll have to come up with two directions. So what will be the forward direction? Right? Or a MST with all the properties. Okay, yeah, that's exactly right. So let me reiterate what you just said. So the forward direction is basically, if the algorithm returns not possible, that means there exists no spanning tree of G where all vertices in S are leaves. Okay. Similarly, in the backward direction, what it is saying is like, if the algorithm does not return not possible, that means it returns false. It returns true basically. That means there exists a spanning tree of G where all vertices in S are leaves. Right? What you said, it was actually a contrapositive of the backward direction, but they all mean the same thing. So let's see how we'll prove the forward direction. So first, what we'll do is, so the first thing is like we are saying like it returns not possible. So when is it the case that we are returning not possible? That's yeah. So the algorithm that we had, we first check the if everything is connected after removing all the vertices in S, right? So that was the first possible scenario in which we will return not true, right? So yeah, that's exactly what our case one is. So the first case is basically when G is disconnected. In that case, we are saying that it's not possible to create such an MST. So how will we prove this? Let's prove it by contradiction. Let's say like there exists a solution like that. Okay. So if there exists a spanning tree where all the properties are satisfied, that means like S are basically a leaf. Okay. And if we remove these leaves, what will happen? All the vertices that we have left, they are still connected, right? Because we are just removing the leaves. So we are not actually breaking the continuity of this whole spanning tree. So what I'm basically saying is, so let's say this is your MST. I just create nodes like this. So what it is saying is remove these leave nodes here. I mean these things. So if you remove these things, it is still a connected graph, right? You'll have a connection between these three nodes. The nodes that are still there in the graph after removing these things. So that means it's a contradiction, right? The graph is actually connected. Like if it is the case, then the graph is actually connected. Is it clear why this first case holds true? Any question? Okay. And what was the second case? Okay, let's take a look at the algorithm again. Okay. So the first not possible was here, and the second not possible was here. So what we are saying is like, if no such edge exit for any of the vertex in set S, right? So means like we have found a vertex S such that there is no way of connecting it to the MST that we have created from G prime. In that case as well we return false, right? Not possible. So this is the case 2. So what we are saying is the algorithm returns not possible after finding that there are no edges connecting some vertex S in capital S to a vertex in T prime, right? In that case we will return not possible. That means like there is some vertex S and it has no connectivity to this T prime. Right? It has no connection to this T prime. In that case, like it's not possible to create a MST satisfying such property, right? Because it can only be connected to some other vertex S1 which is part of S itself, right? And we don't want that, because if that happens, that means it's not a leaf node anymore. Make sense? So we'll also prove this using contradiction. So what we are saying, like assume there is a spanning tree where all the vertices in S are leaves. Then S must be connected to one of the vertices in T prime, right? That's what we are assuming. And because if S was connected to another vertex in S, then it would not be a leaf. Exactly what I said here, that it has to be connected to T prime and not a vertex in set S. Otherwise it won't be a leaf anymore. And this contradicts with the assumption that there are no edges connecting to T prime. Right? Is it clear, or do you need more justification for this? So that's why if we are not able to connect S to T prime, then it's not possible to create such an MST. Okay? So this is it for the proof of existence. So that means like we can create a spanning tree which follows those properties, right? And in case we don't, then it will return not possible. We did not prove the backward direction. Okay. So in backward direction, what we want to show is like when algorithm does not return not possible, that means it is possible. Then there exists a spanning tree G where all vertices in S are leaves. So how will you prove this? So if it is returning it is possible, that means there is still continuity in T prime, in G prime, right? Otherwise it would have written not possible in the first go. So that means there is indeed a MST T prime which is connected. And the second thing is like there is some edge that connects each vertices in S to some vertex in T prime, right? So this is the property of the algorithm itself. So this must mean that we have a spanning tree of G where all vertices in S are leaves. Why? This is because T prime is a spanning tree of G prime, and that means there are no cycles in T prime. And when we connect these vertices from S to T prime, it's not creating any cycle either, because we are not connecting the vertex in S to a vertex in itself, right? We are only connecting it to T prime. So that's why no cycle, and it has to be a spanning tree. We haven't proved that it is a minimum spanning tree. Right now we are just focusing on existence, that it exists, like such spanning tree exists. Is it clear? Any questions, anything like that, please feel free to ask, any doubt. Okay. So now we'll look at the proof of optimality. So now what we are saying, like the spanning tree that we have found, we want to prove like there is no other spanning tree which can give us a better result. Okay. So how will we prove this? So we will prove this using contradiction. This contradiction is a very helpful tool which is used in lot of proofs basically. So what we are saying, let there be a minimum spanning tree L, which is the best answer that you can get for this question. Okay, and it will follow all the properties and the cost will be as low as possible. So this is by definition what we are saying, right? Cost of that L has to be less than the spanning tree that we have found. And the second, so now what we'll do is, so once we have this L here with us, what we'll do is like we will remove all the vertices from this L. Okay, all the vertices in set S, and we will create this L prime. We'll do the same for T. We'll create a like this. Okay. So by definition, we know that this thing here is the MST itself, right? Because that's what we are doing. This T prime was found by running the Kruskal's, right? After removing all the vertices S, we ran the Kruskal, and that's how we got this T prime. So it is the minimum spanning tree on, so T prime is basically a MST on V minus S. That's correct, right? That's what we did in the algorithm. So that's why weight of T prime has to be less than weight of L prime, because L prime is also nothing but connecting the nodes in G prime, right? Because we are removing S. So are you okay with these two things? Like, did you understand how we got this? Okay. So this was by assumption, like we assumed L to be the actual answer, and this is because of the correctness of Kruskal's. So that's what we generally do in the proof of optimality. We use one of the algorithms that we have already learned, and we use the property of that algorithm. Okay, so that's what we are doing in the second case here. And when we put these two things together, what will happen is like, so now you are trying to restructure this thing. Now you are trying to restructure your T from your T prime. That means you are trying to add your vertex, your S to T prime now. Does that make sense? So what happens here is that since L is found by connecting vertices in S to L prime, this implies that there exists some vertex set S that the edge connecting to L prime is strictly lighter than the edge connecting to T prime. And that's not possible, because in our algorithm we were connecting only those edges which was the lowest possible edge, right? So the strictly less than property, it won't hold true, and that's a contradiction in itself. So what we said is not possible. Like, there cannot be any L which is giving you a better solution than T prime. At best it will be equal to your T. Does that make sense? And that's how we prove like the MST that we got is actually the best possible one. Any questions? Anything? I can go over the nitty-gritty of the proof again. So all good? So I think we have time for one more question. So let's take a look at one more example. But I will wait a little bit, like couple of seconds, so that you can absorb this whole thing again. Okay. So what we did, we proved two things. So first we modified our graph. We created an algorithm. For the proof of correctness, we did two things. First one was we proved the property existence. Okay. And the second property was the optimality that we proved. For existence, we used bidirectional proof. And for optimality, we showed it using contradiction. Great. Oh yeah, very important thing, runtime analysis for this algorithm. So the runtime would basically, so let's break it down into a couple of steps. So creating a graph G prime is O of V plus E. Okay. And running Kruskal's is this thing, E log V, because so since we have MST, E has to be big O of V, right? So that's how it comes. It's very similar to your Dijkstra's. And then connecting your vertices in set S to T prime is basically V of E, right? Given that you can do the lookup in constant type if it is a vertex in set S or not. So adding everything, we get this thing here. Make sense? I think the only detailed thing that we haven't discussed is this part, how we get this thing. But it's not that, it's a little bit trivial, because once you have your vertices and edges, the max time that you will take is just go over all the edges and see like what is the minimum possible thing. Right. So yeah. So this is the second problem that we'll look at. So the problem, it goes like this. You are running an energy network given by a connected undirected graph G. Each edge has a positive edge weight that represent the maintenance cost of that connection. There are two vertices, X and Y, that are energy sources. You wish to cut as many edges as you can so that the cost of the network is minimized, but each network is connected to at least one of the energy sources. That means either X or Y. Each node has to be connected to either X or Y. So you want to design an algorithm that determines the cost of resulting minimum cost network. So you basically have a network and you want to delete these edges in this network in such a way that each node, it is either connected to X or Y. And you want to find minimum possible set in this case. I mean, the cost of maintenance should be minimized. That means the sum of remaining edges should be as low as possible. Is it clear? Maybe you can take a couple of minutes to think about it, and then we'll discuss about it. And it doesn't have to be connected directly. That means even if there exists a path through which it is connected, then also it's fine. So what I mean by that is, like, let's say there is X here, you can have A and then B. So both A and X are connected to X. Both A and B are connected to X. So what you want to show is that every vertex is either connected to X or Y. So think about like how you can modify your graph, and then maybe run some MST algorithm, maybe Prim's or Kruskal on that, which maintains the property, and it will also give you a minimum spanning tree for this solution. Should we go over the solution? Okay. First, let's take an example and let's see like what is the minimum cost for this one. So this is your X here, and this is your Y. So what is the minimum possible answer? So let me create one graph. So one way is to create something like this, and then have Y connecting to all the other things. This is valid, right? Everything is connected to either X or Y. So what is the cost in this case? This is 1, this is 4, 5, this is 4. So it will be 15. Can we do better? Yeah, tell me. EY with EB, okay? So you are saying to go like this. But you also need to connect D, right? So only one possible way. So you are saying this is the minimum one. What is the cost in this case? Sorry, what do you say? Yeah, right. So 12 is less than 15. So yeah, this is indeed the answer for this one. So we create it like this. It's a valid graph. Every node is either connected to X or Y, and I don't think we can do better than 12, right? So what should be the resulting minimum cost network look like? And how can we create such a network? So like, what does it look like? So what does the solution look like to you? It's basically two trees, right? Two disjoint trees. In one tree we have X, in other tree we have Y, right? That's what we saw in the previous example as well, right? That's what the solution generally looks like. So we want to show like that property actually holds. We will indeed get two trees. In one tree we'll have X, in other tree we'll have Y, okay? So the algorithm, what is basically is telling you is to do something like this. So we create a dummy edge XY with weight 0. It's a very smart trick actually here. What we did here is like just connect X and Y with a 0 weight edge, yeah? And then run the Kruskal on that graph. And once you have a Kruskal on that graph, you just remove this thing back from the solution and you will have two different trees. Like intuitively it makes sense, right? This will give you a solution. And like if you think intuitively why it works is like when you run Kruskal on this one, this edge 0 will always be picked first because it is the lowest possible edge, right? So it will always be part of that MST, and MST is nothing but a tree. And if you break even a single one, which is not a leaf edge, then it will break your MST into two different trees, right? Does that make sense? So let's see the proof. So first we want to show that the optimal solution must be two trees such that X is in one tree and Y is in the other tree. So assume that we have such network, okay? So first we will show that each vertex has a path to either X or Y. So that means it's a valid tree, right? Because we are in the solution in the MST, everything will be either connected to X or Y. So if we add any other edge to that set, it won't give us any extra benefit, right? It will just add on to the cost, right? So we don't have to add. So there is no need to add any other edge to this whole thing. It's not giving us any benefits, right? The property is already achieved, and there is some cost. Why add extra edge to it, right? And what about, can we remove some edge from this set? Can we like make it even better by removing something? So what happens if you remove some edge? If you remove some edge further, that means it will further disintegrate that tree into multiple tree, right? And the connectivity will be broken. Because in the MST, even if you remove a single edge, that means it won't be connected anymore. Does that make sense? So I think it's the best, is the most suitable solution that we have, right? We have no need to add or either remove, right? Is the most concise thing that we have achieved. So let's see the proof. Here also we have to show two things, existence and optimality. In existence, we will show that there exists a valid graph, valid network with the total cost returned, okay? And in the optimality, we will show that the cost that we got is indeed the lowest one, is indeed the minimum possible cost. So how will we prove the existence property? So algorithm found an MST of G prime using Kruskal's, which necessarily contains the edge XY, right, with weight 0. Why? Because that is the first thing it will pick. So the edge with weight 0 will always be there in the MST. So this is because the same thing that I'm just reiterating over it. And given that all the other edges have weight 1 or higher. So first thing achieved, right? Existence property is there. So that's why the solution exists, because the 0 will be picked first and we just have to remove the 0 in the end. So let's see. So let the MST of GBT, the G of G prime BT. What is G prime? It is just G plus XY, right? This is with weight 0. This is what G prime is. And now if we take the 0 edge weight away, the resulting graph is a forest F, of two vertices of two trees x and y, such that x is in x and y is in y. The sum of the weights in T and F so what it is saying basically is, so we'll get F, it is these two trees, x is in one of it and y is in one of it. So cost of T will be equal to, maybe I should write this neatly here, it will be cost of T will be equal to cost of F, right? Because we only added like edge weight 0, so they are same. And we already show like such a graph is valid, right? And so there exists a energy graph with total cost equal to the one that algorithm returns. Is it clear till now? Any clarification required? Please let me know. Okay. Sometime it might happen that I prove it in my head and might not say it out loud. So if there is anything that you think like, even if there is a small gap in the bridge that you are having difficulty to connect, let me know. Okay. Should we go ahead? Yeah. So now we want to prove the optimality proof. So we showed like whatever we get, it follows the property and it will give us some cost, right? So what if we follow this algorithm, then we will indeed get some solution that follows all the properties. But now we want to show the cost is the minimum possible cost. So how will we show that? So here also we will take help from contradiction. We will try to prove it by contradiction, and we'll say like there exists a better network, right? So what we are saying is that let's say this F prime is the better network that we have, but this F will still follow the property that there will be two different trees, right? That's what we followed. Every solution will have to follow this property that we get two trees. In one tree we'll have x, in another tree we will have y, right? So these things will look something like this. And now by assumption we said like weight of F prime is less than weight of F. That's what we're saying by assumption. So what will happen here? So now let's create T by adding this edge x to y, and let's create T prime by adding this weight x to y in T. Wait, what was the notation? Yeah, we create this x y, and the new graph we are calling them T prime and T. Okay. So what happens here? So the by correctness of Kruskal, we already know that weight of T has to be less than or equal to T prime, right? That's correct, right? Because we ran Kruskal on this graph. So that's why this property has to be there. So the cost of this thing has to be less than T prime, right? That's what the Kruskal is. So this will also be true. So weight of T is nothing but weight of F plus this edge here, and weight of T prime is weight of F plus again 0. So these two things are same, these two things are same. Now we just have to put everything together and see if it makes sense, right? So this is what we are like putting everything together now. All the things that we just showed in the previous slides, we are just putting them together, and we are seeing like if it is still consistent. And it turns out it is not consistent. Why? Because what we showed here is like weight of T is less than or equal to weight of T prime, this thing, by the correctness of Kruskal, and weight of T is nothing but equal to weight of F prime, this property here. Because adding extra weight 0, it won't increase the cost of the graph, and it has to be strictly less than this graph F. That's what we assumed, right, from this property. And weight of T is nothing but equal to weight of F, because we are just adding a node, an edge with weight 0. So this is true. But what happens is like there is inconsistency. Why? Because of this thing here. It is strictly less than or equal to weight of T. And it's not possible, right? So that's why there is a contradiction. And that's why the graph that we have, it gives you the optimal solution. Any doubt here? Is this inequality a little bit confusing? So what we can do is, let's just create it here. So we have t, it is less than t prime, right? First thing. In second one, t prime is equal to f prime. Let's create f prime here. And in third one, what we are saying is f prime is less than f, right? And in the fourth one, what we are saying is t is equal to f. So this thing has to be strictly less than this thing, and it's not possible, right? These two things. Does that make sense? Okay. What about the runtime? Anyone? So what we did was, we just added a new edge. That's it, and we ran Crucible on that. So it will be the runtime of Crucibles only, right? So the total number of edges in the new graph is e plus 1. Vertices still remains the same. So constructing it would be O of v plus e. Crucible is as usual e log v, and adding everything we get this property here. Is it clear? Any questions, anything? I think that was my last slide. Yeah. Oh, right on time. We just have 3 more minutes. I will still be here like for a couple more minutes, and the next session will be taken by Shin. So feel free to wait. If you have anything that is unclear to me, hopefully it will be cleared in the next session. Thank you guys. Thank you for showing up.